My name is CJ Reddy. I'm the VP of Business Development for Electromagnetics at Altair. In today's talk, we'll focus on antenna modeling and simulation techniques. Here is a brief outline of today's presentation. We'll start with the introduction to antenna analysis. Then we'll talk about computational electromagnetics that are key to modeling and simulation. And then we'll go a little deeper into various technologies in CEM for antenna modeling, like full wave solutions, like Metra moments, MLFMM, FEM, and FDTD, and asymptotic solutions, physical optics, ray launching geometrical optics, uniform theory of diffraction, and hybridation of these methods, that is, hybridation of full wave methods with asymptotic methods, and how they can be used for various antenna simulations and modeling. Then we'll talk about antenna arrays, one with infinite arrays, that is using periodic boundary conditions. And then we'll also look at finite arrays with a special technique called DGFM. Not very well known, but I think it's a very effective method for simulating finite arrays, which with taking the mutual coupling into account as well as the edge effects into account. Then we'll briefly touch on advanced topics like characteristic mode analysis and also machine learning for antenna design and optimization. We're not going to go into too deep into these methodologies, but we'll provide references where you can follow up if you're interested. We'll conclude this talk with antenna modeling and simulation in education. It's very critical that the students are trained in a proper way with the simulation methods, so they come out to be the good antenna designers with the good physical insight of the antenna physics. And also, I'll provide a couple of reading material if you're further interested in learning more about computational electromagnetics. Let's take a brief look at the antenna analysis, how it is normally done, and then go to the simulation modeling soon after that. Antenna analysis starts with electromagnetics, the analysis of electromagnetics, the electric field and magnetic field that we're showing here that need to be solved. The relationship between electric and magnetic field and the currents, the magnetic current and electric current and the charges have been formulated by Maxwell a while ago, that is in 18th century, and that's called the second great unification in physics after the first one realized by Isaac Newton, the three Newton laws that we studied in the universities before. Based on Maxwell's electromagnetic principles, the first radio transmission happened on December 12th, 1901, with a very large antenna, 500-foot antenna, because it's a very, very low frequency, where the signal was sent from England to Canada with a distance of 2,200 miles or 3,500 kilometers. This was done by Marconi, and Marconi is very enterprising. He started a company called Marconi Wireless Telegraph Company in Canada in 1903 after 2 years of his first transmission to send communication between the two continents, that is Europe and North America. This was later renamed as Canadian Marconi Company in 1925, and till recently it existed with the name of CMC Electronics, that is Canadian Marconi Company Electronics, and they were making lots of antennas for aircrafts and other kind of modern devices. And a few years ago, it was acquired by a company called Esterline Corporation. So it no longer exists with that name, but it's very interesting to note that what started in 1901 existed for 100 plus years, and of course it's finally acquired by a bigger company. While Marconi was doing his experiments on RF wave propagation over the ocean, a well-known Indian scientist, Jagdish Chandra Bose, he demonstrated in November of 1984 that you can ring a bell by igniting a gunpowder and sending a micro signal in millimeter wave range to the bell. At that time, he wrote an essay called Adrishya Lok in his native language, Bengali, which means invisible light, that the invisible light can easily pass through brick walls, buildings, therefore messages can be transmitted by means of it without the mediation of wires. Though it's kind of a visionary statement back in 1894, now it's so true. I think we're all living that dream or vision of last century or 18th century that now we take it for granted, but that it took a bit longer time for us to realize and have it in our daily lives. In September of 2012, IEEE has recognized his work in millimeter band radio and as an IEEE milestone in electrical and computer engineering. This is actually first such recognition for a discovery in India that happened in electromagnetics. Of course, I'm also giving you a link at the bottom. You can read more about it at that link. With those humble beginnings of antennas that started as very simple devices, now they're everywhere that you can imagine. For example, aerospace, automotive, defense applications, communications, consumer electronics, energy sector, and healthcare. Of course, that also makes it very critical that they to be taught well in the universities and educational institutions. So we have people who are skilled enough to design them and also fabricate them and then put them onto these devices and give us the next generation communication devices that we can all use and be productive and also for our own enjoyment in terms of the connectivity, etc. So how do we analyze antennas? One is, of course, based on solving Gaussian equations of underlying physics. These can be expressed in terms of differential or integral equations. And solving these equations requires that you apply boundary conditions of the specific problem that you are solving. Analytical solutions are possible when problems at hand is simple enough and we can apply boundary conditions to them. So the Gaussian equations, obviously, as we mentioned before, are Maxwell's equations. I'm showing here in the middle column the integral form of them, and of course the left-hand side, right-hand side, the differential equations by Maxwell. So electromagnetic field behavior, as we know, is governed by Maxwell's equations. It can be expressed in terms of electric and magnetic fields and the sources, J and M, that is electric current and magnetic current. So you have the four equations that we already seen before, and then you solve them for in terms of vector potential A, and this can be obtained using the free space Green's function G. And using these two things, one can write electric field in terms of vector potential A and also the Green's function G, that is vector potential can be re-expressed in terms of the Green's function and the electric current that is available in that problem. So the complete description of the electromagnetic problem will include information about the equations and also mainly and also more importantly the boundary conditions. That is the tangential component of E field is continuous across the interface and is zero on the perfectly conducting PEC surface. But also the tangential components of the magnetic field is discontinuous across the interface to the extent of the surface current. So these two are the boundary conditions you need to impose when you solve a particular problem using Maxwell's equations to get the electric and magnetic field or to get the electric current and magnetic current. Let's take an example of a simple dipole like the one I'm showing here. Vector potential can be obtained by taking the line current, that is the current along the length of the dipole, and the Green's function, free space Green's function, which is e to the power minus jkr by r. So if the length is very small in terms of wavelength, we're talking about less than lambda by 50. This is a very simple equation because I is constant because of very small size of the segment there or the length of the dipole. So you can simply multiply and have this simple expression that can give you the vector potential, and from vector potential you can calculate the electric field, and from electric field you can calculate the rest of the quantities that you need to compute. But then what happens when the length becomes a little larger, that is lambda by 50 to lambda by 10, there is a linear variation of the current along the dipole length, which means that you will have a little bit more complicated integration that need to be done over the linear variation of the current and obtain your vector potential. So what happens when it is even becomes larger than that, that is greater than lambda by 10, then the current will be behaving sinusoidally on the along the length of the dipole, which means your equation, that integration that you have to do, will get more complicated. But of course, it's not very difficult to do that mathematically. So one can obtain the current distribution like this, and as well as the directivity from the current distribution can be calculated. So same problem can be analyzed with the modeling and simulation using a tool, for example, the Feko, Altair Feko tool that we'll talk about a little bit later. Here, typically it is presented with a CAD interface like the one I'm showing. You can also have variables. That is, you can define your geometry in terms of the parameterized geometry there. And then, of course, you can define the dipole length, whichever you want to define, and discretize it with segments of appropriate number. And then, of course, you can define what are the quantities you want to compute, the radiation pattern, the near fields, etc. And then the tool will compute those quantities for you. And of course, then you can compare your simulated current distribution on the dipole. This is lambda by 2 dipole with the one analytically computed in the last slide. One of the challenging tasks is not just computing the electric field because of the dipole, but also including the surrounding environment into the calculations. Of course, by itself, we can see the radiation pattern is very nice, and typically it is referred to in textbooks as donut pattern because it looks like the donut that we are familiar with. Um, but what happens when you put a conducting cylinder in front of this dipole? What kind of radiation pattern can you expect? This is, one can still, if you are mathematically very astute, you can derive the equations for this. Of course, you can derive equations for the cylinder, a sphere in front of the dipole also. But it is not going to be easy. That much we can say about that. Of course, it becomes a dielectric sphere, that is a dielectric sphere in front of the dipole. It can even become even more difficult or complex because now dielectric sphere has not only the electric current but also the magnetic current flowing around it. Of course, with the simulations, this becomes a very simple task with the modeling and simulations where you can simply model a, a conducting cylinder in front of the dipole, and of course a conducting sphere or a dielectric sphere in front of the dipole, and can compute the fields and radiation patterns as we are seeing here. This brings us to the topic of computational electromagnetics. Computational electromagnetics is nothing but a science of solving Maxwell's equations using numerical methods, which lets us solve different type of problems that we encounter in day-to-day life with less complexity than what it would take with analytical methods. The way the computational electromagnetics work, so you take the realistic objects, anything you can think of as I'm showing here, and then solve Maxwell's equations by the CEM tool, and then get electric fields, magnetic fields, currents, and from there the radiation patterns, input impedances, etc. There. So the CEM tool, which we mentioned it based on numerical analysis, also solves the Maxwell's equations, but may not be analytically, but in a different way. As an example, if you take the realistic object like an aircraft we're showing here, you make a CAD model of that, that is the computer representation of the geometry, and then from there you discretize, that is you make the CAD model into very small triangles, the surface of the CAD model. What that means is that you can see clearly here, we're representing the surface with these small flat triangles. Essentially, the CAD tool or the CEM tool you're going to use, it will solve Maxwell's equations in these small triangles because that's a known shape that we have. So each of those things can be added so that you can get the currents on the aircraft, and from the currents one can also compute the radiation pattern, because here we are solving 120 megahertz VHF antenna, COM antenna on the aircraft, like the one on the top of the aircraft here. So with that, not only that we can solve an aircraft problem, but also we can take an automobile and there's an antenna on the back, normally referred to as a shark fin antenna. So in this case, we took 1.8 gigahertz LTE antenna as an example in the shark fin. And of course, we can take the CAD model of the car, and then you can discretize it. And of course, you can look at the mesh, and then you can compute the currents, and then you can compute the radiation pattern. Similarly, you can take, let's say, a ship on the water, and then you can model the ship geometry with a little bicone antenna at 100 megahertz. And of course, water can be modeled as a lossy surface. And of course, you can discretize with triangles, and then you can compute the radiation, the currents, both on the ship as well as on the water, and then computed radiation patterns. The point we're making here is that once you have the tool, like the CEM tool that you're going to solve, that solves the Maxwell's equations numerically by discretizing it. So any object you bring in, you discretize. Once you discretize, it becomes a known element like the triangle, tetrahedrals, voxels, etc., and solve Maxwell's equations in those small elements and can add them up. So this way, you're not rederiving solutions for every problem that you bring in, and every problem can be solved using this process here. One thing that we need to keep in mind is the how finely you want to discretize, because one of the rules in the meshing is that one, of course, you want to capture when you mesh or discretize your geometry with the triangles or tetrahedrals or voxels, is to keep the geometry shape as close as possible to the CAD geometry you have. The second criteria is to make sure the size of that element um, when added together can capture the current behavior. You can think of it this way, I guess. If you have one wavelength of a sinusoidal shape of a sinusoidal wave of one wavelength, how many points you need to represent that sinusoidal wave? You can say, I can put 2 points. No, it's not going to do it. 3, 4, maybe 6, 7, maybe we're getting there. But let's say approximately 10 would be um, reasonably represent the sinusoidal wave. So in that respect, when you think of the currents that are flowing in on the surface, to represent them, how many points you need per wavelength, that may be the criteria to be used in terms of the how finely you want to discretize or how coarsely you want to discretize your object. So as a rule of thumb, based on the frequency, you can say 1/10 of a wavelength is a good number for the size. So what that means is that your discretization depends on the frequency. So as the frequency goes up, the wavelength decreases. As the wavelength decreases, the size of the elements you want to discretize will decrease. And that means the number of triangles or number of tetrahedrals will increase. That means the amount of memory you need, amount of CPU time to solve that problem will increase. That's where different technologies come into picture, how to reduce the memory you need and the time you need for your problem solution. Altair offers very sophisticated antenna simulation tools. Altair Feko is the leading antenna simulation tool in the world, and it offers various technologies that I'm going to discuss in this talk, including all the numerical methods that we're going to illustrate in this talk are implemented in Altair Feko. So when you have Altair Feko, you have the possibility of using any of them based on the problem that you are solving at hand. So you can calculate individual antennas and placing them onto vehicles like cars and aircrafts, and their effects on the radiation patterns can be calculated. And we have another product called Altair WinProp. This actually implements wave propagation tools as well as radio network planning tools. What that means is that you can, let's say, take the radiation pattern from a car, and then you can put them into a city, drive around, and you can get the connectivity or the signal strengths from a base station, for example. But at the same time, by interfacing with the wireless communication protocols, you can also get the connectivity information like the channel capacity, data rates, and those kind of things. It can also be used for example, the one I'm showing here, the car-to-car communications as well as automated driver assistance systems that are also becoming very popular, and also virtual drive tests, etc., can be used. So these are complementary products. That means you can do very detailed analysis in Feko with antennas and antenna placement, and then you can use that information, there's radiation patterns, to compute a broader propagation analysis and also connectivity analysis. So completing the picture for your antenna design, going from the design of the antenna, placement of the antenna, and its use in the real applications such as a car or an aircraft, etc. How can these tools can fit into antenna product development process? Let's say you have a blade antenna. You design with your CEM tool, and then of course you compute the radiation pattern. As you can see, it's a very nice pattern with no um, what I can call is anomalies or anything like that. It's a nice donut pattern, half donut, because it's in an infinite ground plane. Then you want to place it on a vehicle like a helicopter, for example. I'm just showing this as an example. Put this blade antenna on the back of the fuselage of the helicopter, and then you compute the radiation pattern. Now we can see that there are many different nulls and different peaks because of the interactions with the helicopter body as well as the blades, rotating blades, etc., in this problem. So you can see that the nice pattern does not remain nice anymore. So that's why it's critical to compute uh, the the antenna pattern on the platform on which it's going to go. So now we can take this helicopter and then actually do a virtual flight test in a city environment. This is the flight path we're talking about for the helicopter, for example, and there's a base station that's communicating with the helicopter, and this colors here show the power density as helicopter is moving in this path. As you can see that initially it's a little bit high, a little bit low, high and low, but the moment it goes behind this building, it kind of fades out and then comes back again here. So in this case, of course, you can use Altair Feko. This is the one I talked about before for antenna design as well as antenna placement. But of course, you can use Altair WinProp for the placement for the virtual flight test of this helicopter with the antenna on it. Similarly, another case study for the product design, if you have a mobile device, so you want to put antennas into the mobile device and compute its radiation pattern as well as for the base station as well. And then you can put the base station into the city, and of course the mobile device going around in the city and its connectivity because of the power density that you want to compute. And same thing with the Wi-Fi router, and then in indoor environment, you want to be able to compute how the connectivity of the mobile device inside the indoor environment based on the placement of these Wi-Fi routers. These blue dots here indicates the placement of the Wi-Fi access points inside the building. Again, here Altair Feko can be used for the device modeling as well as the base station and Wi-Fi router modeling, and of course WinProp for the propagation and network planning. That is, if you have the protocols of your Wi-Fi protocol in the indoor environment, we can compute the connectivity at the data rates, etc. Same thing with the outside. If you have LTE or 5G protocols, we can compute the data rates for those protocols. Now let's take a look at the various CEM solver technologies and how they can be used for different antenna analysis and design. As we use different CEM tools for solving and modeling and simulation of antennas, it is very necessary that we have some basic knowledge of CEM solver technologies behind those tools, because each of the solver technology brings certain advantages for certain class of problems and disadvantages for other class of problems. So having known the advantages and disadvantages, it will help us apply these methods intelligently to those antennas and antenna designs that we need to do. So broadly, we can categorize these solution technologies as full wave solutions and asymptotic solutions. Full wave solutions means we solve Maxwell's equations accurately and provide reliable answers provided you have a good CAD model, the one we showed before, and also a good mesh for the CAD model. By that we mean a mesh that captures the geometry details, but also a mesh that is suitable for that frequency of operation. Asymptotic methods also solve Maxwell's equations, but with appropriate assumptions and approximations. So they also can provide reasonably good answers, or I would say accurate answers, provided we know the approximations and assumptions and we are applying them appropriately for the problem at hand. So full wave solutions include method of moments, multi-level fast multipole method, finite element method, and finite difference time domain method. Of course, there are other different variations of these methods also can be called full wave solutions. Asymptotic methods include physical optics, large element physical optics, ray launching geometrical optics. This is also sometimes known as shooting and bouncing ray or SBR technique, and uniform theory of diffraction. So while we can apply full wave solutions for all problems because they're accurate, but they can be computationally very expensive when applied to electrically large structures. So in this way, that's where we may need to apply asymptotic solutions as an alternative, but asymptotic solutions may not be valid for complex antenna geometries. So that's where the hybrid solutions that combine both full wave solutions and asymptotic solutions can facilitate the simulation of electrically large antenna problems with less computational resources, at the same time providing the accuracy needed. In terms of hybrid solutions wise, we're going to talk about these methodologies in this current presentation. That is FEM hybridized with method moments and MLFMM, as well as method moments with the physical optics, MLF with the physical optics. Same thing with LEPO and as well as RLGO and UTD solutions. This can be pictorially represented in this diagram here, where the our horizontal axis here is the complexity of materials and vertical axis is the electrical size. As you can see, FEM can be very good for electrically reasonably small sizes, but at the same time inhomogeneous, a lot of inhomogeneous materials. Same thing with FDTD, but electrically limited in terms of not that they're not valid for electrically large structures, just that they become computationally expensive. Then one can apply method moments, little electrically larger structures, but less complex, and then MLFMM, even higher in electrical size. And then comes the asymptotic solutions, physical optics, ray launching geometrical optics, as well as uniform theory of diffraction. And these arrows represent hybridization of FEM with method moments, FEM with MLFMM, and so on and so forth, method moments with physical optics, and UTD and RLGO. And one other method I have not mentioned, I won't talk too much about it in this talk, but that is also becoming very powerful is ACA, adaptive cross approximation. This actually solves the method moments matrix in a way that you can reduce the memory and the CPU time that is needed to solve a method moments matrix. If it is large size of the matrix, where MLFMM may not be applicable. So we're going to talk about those things as we go through various methods in this talk. This chart actually illustrates why we need different methodologies for a different class of antennas when we simulate them. For example, wire antennas. Method moments and MLFM can work very nicely for these type of wire antennas. Planar antennas. One can use the planar Green's function method, which is similar to method moments, and method moments FEM or FDTD based on the number of materials you have, the complexity you have in your antenna structure. When it comes to antenna arrays, again, you can use planar Green's function or method moments, MLFMM or FEM or FTTD, again based on complexity of your array structure. Also, as we discussed before, the DGFM methodology can also be used for finite array analysis. Extending this further, for example, horn antennas and lenses, reflector antennas, this is where the asymptotic methods can come into picture. Even the lens antennas, for example, you can apply RLGO very effectively for lens antennas. Same thing with the reflector antennas, PO and LEPO and RLGO become very attractive in terms of computational power. When it comes to mobile and wireless antennas, method moments can be used. FEM and FTTD also can be used based on the complexity of material. First, let's take a look at full wave solutions. Full wave solutions can be divided into two different categories. One is called field method, where we solve differential form of Maxwell's equations. Other one is called source method, where we solve integral form of Maxwell's equations. So in the field method, we solve for electric and magnetic fields, whereas in source method, we solve for the currents, that is electric current, magnetic current. Of course, as we mentioned, this is a differential form of equations, this integral form of equations. When it comes to discretization, that is meshing, this will be volumetric. Field method will be volumetric like tetrahedral elements or voxels, whereas in the source method, it's a surface discretization, that is segments and triangles. When it comes to radiation boundary in the open problem, that is when something is radiating into an open space, we would need special absorbing boundary conditions, commonly referred to as ABCs, in this form of solution because they don't inherently include the radiation boundary into the formulation. Popularly known as air box around the radiating structure. Whereas in the source method, radiation boundary condition is already taken into account in the formulation, so you don't need the air box to be put around the problem of interest there. So the methods that fall under the differential form of Maxwell's equations is FEM, finite element method, and finite difference time domain method. So when you use these methods, when they're used in a closed problem, by that we mean something closed in a, let's say, perfectly electric conductor that is not radiating fields into the open space, they can work quite nicely and they don't need an air box. But if you are using it for radiating structures like antennas, they would need the air box to enclose that computational problem. So the air box acts like you can think of as an anechoic chamber, numerical anechoic chamber, where the waves propagate up to the boundary and they don't reflect back to the problem. Of course, there'll be some reflection. That's why you have to keep the air box slightly away from your radiating structure. In the source method, method moments, adaptive cross approximation, MLFMM fall under that, and you don't need the radiating box. So there are some advantages in using FEM and FTTD based on what type of problem you want to solve. Of course, there are some disadvantages like having to use the air box around the radiating structure and also having to discretize the whole volume if it is needed or not in the differential form of Maxwell's equations, that is FEM and FTTD. Whereas method moments, MLFMM, you don't need an air box You don't need to volumetric discretization. So in some problems, it could be very, very easy to solve and also less computationally expensive compared to FEM and FDTD. Of course, it has got its own disadvantage when the structures become electrically large. Let us start looking at these full wave methods one by one. And the first one we're going to look at is method of moments. So method of moments, as we mentioned, is a surface method. That is, you take a CAD geometry, for example, this horn antenna, create the CAD model, and of course apply the surface mesh. You don't need to discretize the volume, or you don't need to put a air box around it. So just a surface mesh is good enough, and we apply boundary the basis functions, normally referred to as RWG basis functions, and solve the linear equations that are formed. So the linear equations that is formed by method of moments will look like this. That is Z multiplied by I equals V. Z is sometimes referred to as impedance matrix, nothing to do with the antenna impedance. That's how they named it when they formulated this. Typically, is the n by n complex vector. That is, n is the number of unknowns on this problem. And so it forms an n by n complex matrix. I is an unknown vector. There's a current that you need to solve. V is the known excitation vector. That is for example, you have a voltage gap source or the modal port. Those things form the V, that is the known source. And then you could solve this equation by taking the inverse of Z, multiplying by with V, and you get a solution. Of course, typically in method of moments, use popularly known as RWG, Rao, Wilton, Glisson basis functions. Basically, these basis functions show that the current will vary linearly from this vertex all the way to this edge, and then of course decrease from this to the other vertex. Sometimes these things are called rooftop because they look like a roof going from here to here and back to here. Same thing on the wire segments. Use a triangular basis function that goes from one end of the wire to the middle of the end of that wire, and also to the other end of the wire, and then so on and so forth, the superposition of these triangular basis functions. Basically, the meaning of these basis functions is to explain or provide the behavior of the current in that small triangle or a small segment. So the better you can explain, the the less number of unknowns you can have. That's where the higher order basis functions come into picture. But for the sake of our presentation here, let's say we use RW basis functions. So each of the unknown associated with this edge, and of course here each of the unknown is associated with this node here. So once you have those unknowns solved, this I vector here, they form the amplitude of these basis functions, giving you the current distribution on a wire segment here, or on a horn or a 3D surface, in this case for the surface problem. This chart actually illustrates once you solve for the currents, of course we can plot the currents on the surface, you can compute the near fields from these currents. Also from these currents, you compute the radiation patterns, you can compute the S parameter, anything you like, I guess. Once you have the currents, you can compute all the quantities you need for your problem. Let's take a look at some examples for method moments. One I took as a first example is wire discone antenna. One of the reasons is because when you have these wire segments, wire type of structures, method moments can be the best solution you can have, because you don't need to model these wires as cylinders. You just model them as thin wires. That is what we call thin wire approximation. So basically, they are linear segments that are discretizing the wire. And the same thing with the ground plane as well. If the ground plane is of a wire structure, so all of them are wires. So you can see that the number of unknowns can be very, very low for this type of problem. So we're just solving this at 50 megahertz or over a wider frequency range here. So you can see the S parameters and the radiation patterns at 60 megahertz as well as 110 megahertz. So making this a little bit more complex, we go to broadband helix type of an antenna. Again, here this is a wire structure, helix itself, but there's a finite ground plane that's a surface. So we simply have to mesh the surface with triangles, and then these wire segments can also be curvilinear so that you don't have to use a lot of segments to create a very nice helix structure here. That's one of the advantages again for metro moments, that you don't need any air box around it. You don't need to approximate the wire with a cylinder with tetrahedral meshing and other things. All it needs is a surface triangular mesh and linear segments, curvilinear one in this case, to model this helix. Now we can compute the radiation patterns as well as the reflection coefficient or a frequency band with very, very less computational cost and CPU time. Making this a little bit more complex, we look at printed log periodic antenna. So typically, these are also done with wires, but sometimes for the sake of stability and also conformability, these are printed onto a dielectric substrate. So method can also handle dielectric structures like this one we're showing here, as well as the metallic patches on the dielectric surface. So this is actually done with 4.35 dielectric constant with 18 elements of the log periodic with a center frequency of 1 gigahertz, um, typically to obtain around 9 dBi gain. So here you can look at the currents on the surface of the antenna at 650, 1 megahertz, and 1.350 megahertz. You can see that here, as a lower frequency, you can see the currents spread over the structure. As you go to higher frequency, they go to the higher end of the antenna here, and of course more here. And you can also see it's around 50 ohms input impedance, and of course close to zero with the imaginary part. The real part is close to 50 ohms, imaginary part is close to zero, and the radiation pattern looks nice as an omni pattern that we normally expect from a log periodic antenna. One more example with meta moments, that is coplanar waveguide fed bow tie antenna structure. So again, here you can see that we can model the dielectric and also the ground plane here, and also fed with a edge port here for this structure. And of course, you can also refine the mesh where the current density is expected to be more, and also variation is expected to be more here, and you can see the VSWR. So just illustrating that method moments can handle different type of problems, antenna problems that we come across in our work. By now we got the point that method moments is capable of handling different type of antennas that we showcase so far. So as one last example, I wanted to show a single patch that's on a finite ground plane, and it's radiation characteristics at 1.62 gigahertz. At both principal planes, they look very symmetric because structure is symmetric, and the currents, surface currents, as well as the radiation pattern. You've seen the simulation of single patch antenna on a finite ground plane, the previous example. Now let's take 106 of them, put them on a panel for this size, 1.8 meters long, but 0.8 meters wide, and of course 0.048 meters in thickness. Of course, this is where still solving at 1.62 gigahertz. So if you mesh this whole panel with the triangular surface mesh, it results in 47,148 triangles, which amounts to 131,565 unknowns, which means, as we have seen before, this is if this is n by n complex numbers. This is a complete matrix with these numbers that requires a memory of 125 gigabytes. Just for the sake, of course, we can go to bigger computer and solve this with no problem. But I'm just using my desktop, which has only memory of 64 gigabytes. So obviously, I can't solve this problem with 125 gigabytes. Maybe I can solve it using my out of core solution onto the disk, but that's going to take a long time because of the disk speed and all those things. I would like to be able to solve this faster than that and with less memory than 125 gigabytes. That's where MLFMM comes into picture. So we'll talk a little bit about how MLFMM can reduce the memory and time requirements for electrically large structures like this one here, and see how this problem can be solved with MLFMM with less memory and CPU time. If I have not already mentioned, MLFMM stands for Multilevel Fast Multipole Method. Of course, you can say many times as Multilevel Fast Multipole Method, MLFMM. To understand the need for MLFMM, we need to understand what makes method of moments expensive, computationally expensive. As we already mentioned, we need to solve this matrix equation ZA equals V. That means we have to invert the matrix Z and then multiply with V. Of course, it's not a big problem. Mathematically, we have learned these things even in our high school, I guess, how to invert a matrix and multiply with a vector and get a solution I. But the problem is that LU decomposition of this, that is this inverting of this matrix, requires order of n cubed operations, and storing the matrix require order of n square memory, that is storing the whole matrix where every element is a non-zero quantity in this matrix. So we need n by n memory requirement, order of n cube operation count requirement. What does that mean in terms of real numbers? That is order of n cubed versus order of n square, etc. What it means is that let's say you have a structure like what I'm showing here, and you discretize this for 1 gigahertz for the sake of argument. And if it resulted in n triangles or n unknowns, if you double the frequency to 2 gigahertz, the number of unknowns will be 4 times n. That is because of surface. So you're increasing 2 times on one side, 2 times on the other side. So it becomes 4 times, 2 by 2, 4 times because it's a surface. So what that means with the n cube, that is order of n cube, means it's 64. That means if it took, let's say, 1 hour to solve the problem at 1 gigahertz, it will take 64 hours to solve at 2 gigahertz. And if it took 1 gigabyte to store at 1 gigahertz, it will take 16 gigabytes to store at 2 gigahertz. So that's not a scalable thing, because once you increase this 2 gigahertz to 4 gigahertz, your number of hours will go from 64 to 64 multiplied by 64. And of course, if we make it 8 gigahertz, it'll be even a larger number. Same thing with the memory. So very quickly, you're looking at days, weeks, months, and in cases years. And of course, it can span one's lifetime as well. While hoping that you still have the memory to store that kind of a matrix, but we only increase the number of unknowns by 4 times. So in a practical sense, we want to only go linearly increase our memory and CPU time with respect to number of unknowns. That's where MLFMM comes into picture. So essentially what MLFMM does is that when you have a object that discretized like this one, it divides this mesh into smaller boxes like I'm showing here. And then it looks at each box and says, okay, this box is close to next box. So let me compute the interactions as though I'm doing a normal method of moments calculation. That means each triangle in this box will be interacting with the other box, etc. But let's say I take one box here and one box here. They're electrically far away, so I don't need to consider each triangle, but I can take the total effect of this box and the total effect of this box here. So that's what we call aggregator operator, that makes all the effect of these triangles in this box to be one number or one quantity. And the same thing here on the other observation side, a deaggregator box and a translator operator. So if there are 1,000 triangles here and 1,000 triangles here, instead of forming 1,000 by 1,000 interactions, I'm only forming a 3 quantity interaction here, A, D, and T. That's how MLFMM reduces the memory and also the time required for your calculations. Of course, this I'm explaining this, but in a tool like, let's say, Altair Feko, this is all internally taken care of, and you don't need to be concerned about how these boxes are made, how the interactions happen. I'm just letting you know that this is how MLFMM reduces the memory and reduces the CPU time. So with those operations we have shown in the previous slide, now MLFMM scales with respect to memory at 5 times than 4 times, and of course 6 times for the CPU time instead of 64 times, and 5 times rather than 16 times in terms of memory wise. Now we are talking about affordable way of increasing your frequency range for the same problem on your computer with the same memory and with reasonable time. You should be able to get your answers. Now let's take a look at the example of the microstrip patch array that we left off with method of moments with 106 elements with the large panel, electrically large panel at 1.62 gigahertz. It's the same array, same size, same mesh with 47,148 unknown triangles and number of unknowns 131,565 with the same matrix size where method of moments required 125 gigabytes of memory. Now with MLFMM, the procedure that we talked about, you can solve this problem with 11 gigabytes. Remember the desktop I mentioned that only has 64 gigabytes. So we have plenty of memory to solve this with 11 gigabytes. And of course, time-wise, it's only 10 minutes to solve this problem. We can look at the surface currents and also the radiation pattern of the array and a pattern in both principal planes, that is phi equals 0 and phi equals 90 degrees. Now that we could solve this problem, the panel, we went a little bit ahead and then said, okay, let's put the whole platform here. That is a satellite. Actually, this is a part of a satellite antenna array that is on each panel. For example, you can have another antenna array here, another antenna here, and another one the other side. So of course we took one panel and then put all the patches there. And this is the mesh at that frequency 1.62 gigahertz. Now it's number of unknowns. The triangles are going to be 216 or 217,000 triangles that result in 376,722 unknowns. If you were to solve this in method of moments, it would take 1 terabyte. Because we're not talking about the time here. Time could be even higher, much more than what we can think of. Again, here this was solved in 11 gigabytes in 47 minutes. Because it's a little bit more time, 11 minutes to 47 minutes with the whole satellite structure here. You may be wondering why it took only 11 gigabytes versus the other case, which is still 11 gigabytes just for the panel. One of the reasons is because MLFMM gets more and more efficient memory-wise as you increase the electrical size of your object. So in this case, there being a larger size problem here, and of course there is one panel here, the number of boxes can increase. The number of boxes in the faraway distances interacting with each other can be more. That can result in very efficient, memory efficient solution of your problem. You can see the surface currents as well as the radiation pattern of the satellite array here. Another usual electrically large structures we deal with is with the reflector antennas. So MLFM is quite suitable of doing this kind of structures. In this case, we're talking about 12.5 gigahertz frequency offset parabolic reflector, including the supporting structure. So everything is taken into account, and it is the frequency 12.5 gigahertz at the 18-inch aperture. It's 19 wavelengths in aperture size, 94,000 unknowns, 1.2 gigabytes of RAM, and method of moments would have taken 134 gigabytes of RAM as we have seen before. With that, now we can go to 27 wavelengths is 2 gigabytes of memory, 28 wavelengths, 4.5 gigabytes, 60 wavelengths, 12 gigabytes. So you can really take large reflector antennas and do a complete analysis, including the supporting structures using MLFMM on a reasonably decent computer. Now, let's take a look at the volumetric methods, finite element method, and FDTD next, and then go to the asymptotic methods after that. As we discussed before, FEM or finite element method is a full wave method, solves the Maxwell's equations with volume discretization and generates a sparse matrix, the one I am showing here. It's well suited for highly inhomogeneous regions. So each tetrahedral you can assign a different dielectric material. So it can be as inhomogeneous as you want to be. And of course, you can also include 3D anisotropic materials because the formulation is very straightforward in FEM. So it can also be memory efficient because of the sparse matrix we have. Disadvantages, numerical dispersion. This is when you keep on increasing the mesh size or mesh volume or the problem space. There could be some numerical dispersion involved, which could create an error in your numerical solution. And of course, as we mentioned before, the entire problem space need to be discretized. Um, what that also means that it requires a large set of linear equations. Nevertheless, it's a sparse matrix, but it can become very large. No radiation boundary condition, as we discussed before. That means it requires an air box for radiating problems. One possible solution for overcoming this airbox problem is hybridizing FEM with Method moments. That is, getting the positive side of FEM as well as the positive qualities of Method moments all in one go by hybridizing these two things. What that means is that, let's take this example here as a human body close to a base station antenna here. If you are to solve this whole problem in FEM, you may have to enclose this whole volume in an airbox and discretize the whole volume into tetrahedrals, which means all this empty space or white space also need to be discretized, increasing your number of unknowns. Of course, depending on the distance, if this could be 1 meter away, 10 meters away, 15 meters away, your mesh can keep growing if you were to just use FEM. Instead, you could use FEM inside the human body, but the surface of the human body can be terminated with the method moments boundary condition. That is, the surface, we take the fields inside, that is here, and match with the fields outside with the method moments on the surface. That is, FEM current on the inside to method moments current on the surface. So the radiation boundary conditions taken care of by the method moments currents on the outside. So you don't need to discretize this white space. Of course, the base station antenna, which is a metallic structure, can be modeled with method moments or MLFMM, and the coupling between these two is taken into account. So it doesn't matter now it's 10 meters, 15 meters, 30 meters, 50 or 100 meters. We have the same computational requirement than having the whole space to be discretized. So this gives you the best of both worlds. So you can discretize inhomogeneous dielectrics, for example, human body with the different dielectric constants. You can apply FEM there where it's very efficient. For radiating conditions, you can apply method moments. And also in this case, completely PEC structure with wire segments inside here. If you can see that method moments can suit very well there. Same thing with FEM, MLFMM. You can also, at least in our tool Altair Feko, you can also use MLFMM to truncate the surface structure or the structure on the any other metallic structures nearby. Just for the sake of example, let's take a look at microstrip patch antenna like the one we are showing here. This is a CAD model, and you can also put the airbox around it. And when you discretize it, there'll be tetrahedrals inside this dielectric volume, as well as the tetrahedrals in the air volume here within the airbox. Because you can solve it using what we call FEM only solution, and you can compute the reflection coefficient as well as the radiation pattern. Let's take a look at a little bit more complex problem like this, what we're showing here, where you have a circulator made of ferrite material, and then there is a transmitter and a receiver on these two ports here. So circulator, basically when you transmit from here, the wave goes to the horn side rather than to the other side of the waveguide. And of course, when the wave comes back received, it goes into this arm rather than the other arm. So it provides isolation between the transmitter and the receiver. So here up to this point, it's all closed problem. So FEM provides very efficient solution for this, because you don't need to apply radiation boundary conditions. Whereas from here to here, just a horn, which is an electrically large structure, so you can apply MLFMM, so you can be solved very efficiently. Same thing with the lens, you can apply method moments or surface, what we can also call as surface equivalence method, both to the lens but also an absorber around the lens. So multiple methods can be applied in the same problem, making it very efficient to solve both for memory and the CPU time, rather than applying one method for the whole problem. This is where we can call as one method does not fit all the problems, or one problem cannot fit with one method, where you need to use multiple methods in one problem to make it very efficient with memory and time. Now we can see the waves going from the transmitter going away into the free space. Of course, there's a little less coming to the receiver. Of course, if the waves were coming this way, they would go into the receiver. So it combines the strengths of all the methods together into this problem. One of the last methods we will talk about in the full wave solutions is the finite difference time domain method, commonly referred to as FDTD method. FDTD method, as we discussed before, solves Maxwell's equations in differential form. So uses the volume discretization. It actually uses the voxels like the one I'm showing here. Advantages: it can be used for highly inhomogeneous materials that are in a structure, and also you can have isotropic materials, very easy to formulate. It's also memory efficient because it doesn't form a matrix. Sometimes it's called explicit method because it doesn't form a matrix, and you just take the differences between EX, for example, in this direction, UY in this direction, and EZ in the other direction there. Same thing with the H vector as well. It's also not only memory efficient, but also very GPU friendly. One thing is the GPUs may not have as much as the CPU memory or the RAM. That's why this can fit very well into GPUs, and also the way the differences work can fit very well into GPU architecture or the computational methodology there. So if you have a problem that fits well for FDTD, and if you have GPUs, this is the best way to go. But of course, it has other disadvantages. For example, it has a staircase approximation because of the cubic type of mesh you have to use. If you have highly curved surfaces, the mesh can look like a staircase. And there's a numerical dispersion like FEM, and you have to discretize the entire problem space. And of course, you have to use the air box to contain the radiation boundary condition. It is a structured mesh, which also another word to say it is meshed with cubes or voxels here. Just to illustrate how the mesh for FDTD can look like, if you look at this sphere here, it looks like it's made of little Lego boxes or Lego blocks. So you see these little approximations in the surface. Of course, you can make it finer by creating a finer mesh or the smaller cubes or smaller voxels. But depending on the problem, some approximation or some staircase approximation may be tolerable, but in some cases it may not be tolerable. So as an example, we took same microstrip patch that we analyzed with FEM. Same case here, you use the airbox. Of course, instead of tetrahedrals as we done in FEM, here we use voxels for discretization and compute the reflection coefficient as well as the radiation pattern. Now that we looked at the full wave solutions, let's take a look at asymptotic and hybrid solutions. Motivation for asymptotic solutions is to be able to solve extremely large structures, electrically large structures that the method moments or MLFMM or FEM or FDTD can be able to handle with available resources. That's the key, I guess, here. Of course, there are certain conditions that are applicable to asymptotic solutions. One could be we want the radiated source to be localized and maybe far away from the structure if possible, like the one we are showing here. And structure itself should be electrically large in terms of the wavelength wise, and it's typically used for antenna placement or scattering analysis, but we'll see in this presentation that we can also apply that to reflector type of geometries. Among the asymptotic techniques, let's take a look at method of moments and physical optics hybrid method to start with. This is a one slide on physical optics. Essentially start with an infinite ground plane as we're showing here. And when we have the incident field Hi, that is reflected off of the infinite ground plane and giving us HR, and the current on the infinite ground plane is given by n cross h, the total magnetic field, which can be written as a summation of incident and reflected magnetic fields. So because it's an infinite ground plane and those two are the same value, we can say the current on the infinite ground plane is 2n cross h. So here you know that we know the incident field, magnetic field, we know the normal to the surface, and of course we can multiply by 2 and get to the current. So irrespective of whatever we did in the past in terms of method moments and MLFMM and other techniques, we don't need to form a matrix. All we need to know is the incident field value, and then we can compute the currents. So this can resolve all the issues with the memory and other kind of things. So when people did this, of course, we're not going to use infinite ground for our problems. That's not a problem we want to solve. But even when you make those structures finite, physical optics seem to give a reasonably good answer with this approximation of 2n cross h. So if we can discretize your object with flat triangles, each flat triangle can be considered as a flat plate, and the current can be computed with 2n cross h, where n is the normal to that particular triangle. Then it becomes practical to apply this to different type of problems that we have at hand. But we have to keep in our mind that the origin of physical optics comes from the solution of Maxwell's equations for an infinite ground, and we're taking it to a little bit more further in approximating it and applying it to finite structures. Physical optics can be hybridized with method moments, as is shown in this picture here. You can apply method moments to, let's say, this wire type monopole here and some area around the monopole, and the rest of the structure you can apply, let's say, the physical optics. And we can solve the boundary condition by applying the electric field due to the current on the method moments structure, and also the currents on the physical optic structure, and equals to the minus of the incident field, basically making the total electric field, tangential electric field, zero on the perfect electric conductor. With that approach, we can apply the triangular mesh as we're shown here, and also use the similar basis functions, that is RWG basis functions, for physical optics as well. And of course, the coefficients are calculated by the 2n cross h approximation that we talked about in the previous slides. So one thing to note here is that because of the tight coupling that we have, physical optics unknowns are n and method moments unknowns are m. You will have m by m matrix, that is for the method moments part, n by m matrix for the coupling matrix part. So typically we advise that keep the method moments size as small as possible, so that n by m won't take over your computing resources, as well as n by m, because n is going to be large for an electrically large structure. So even this doesn't take over your computing resources. Of course, in the software, we provide an option you can decouple this, so you don't have to store this matrix where it is not applicable, where the coupling is not is negligible. You can avoid this matrix being computed. As an example here, we can take an offset reflector and apply physical optics onto the reflector structure itself and metron moments to the feed horn. And of course, this is 10 wavelengths long, so 10 wavelengths in diameter. So it's not a huge structure, but still to validate metron moments in physical optics approach as well as working with MLFMM, you can see that physical optics gives reasonably good answers in the main lobe and also well following the trend in the side lobes levels as well. So in case there is a resource, computer resource issues, instead of using MLFMM, one can use metron moments and physical optics approach. Here, taking a slightly different problem with electrically large structures, with a ship with a monocone placed on the deck. Ship is of a length of 200 wavelengths, 23 wavelengths in width, and height of 61 wavelengths. And of course, there is also seawater modeled with a lossy material around the ship. So this would have been enormous amount of computational resources with 3.5 million triangles, but we could solve that with 33 gigabytes of memory and 1.1 hours of the time using physical optics for the whole ship structure as well as the water, and of course metron moments for the monocone structure on the ship. One improvement over normal physical optics, when I say normal, I guess is in the previous slides, the physical optics we talked about requires a lambda by 6 to lambda by 12 element size. So this makes it somewhat unwielding when you go to very high frequencies where, let's say, even if you go with the lambda by 6, you may be talking about millions and millions of triangular elements, which may be difficult to generate for a mesh, may take a long time, but at the same time may take a long computational time when you want to compute the radiation patterns and other things. So we introduced this method called large element physical optics, where we incorporate the phase variation in the basis function over a large the subdomain or the triangle. So you can now have the mesh elements as large as 2 wavelengths and 3 wavelengths. So if your structure geometry permits, you can have less number of triangles, so less number of computing resources and memory for your problem. So we took the same reflector offset reflector problem as we have seen before, applied the large element physical optics to the reflector surface and metron moments to the feed horn. You can see that both methods with the large element physical optics and as well as regular physical optics give almost exactly the same answer. So you can use large element physical optics where it's applicable instead of the regular physical optics. We also took the same example as we have seen for the ship based antenna placement at 500 megahertz, where the ship length is around 200 wavelengths, and the problem is with the 3 million triangles for normal physical optics. Now, of course, we removed the water because large element physical optics is not yet implemented for the lossy water surface here. Even then, this is an electrically large structure with it could have been many number of unknowns with millions of unknowns with regular physical optics. But with the large element physical optics, you can see that it only took 238 megabytes of memory compared to 33 gigabytes for physical optics, and could solve in less than 3 minutes time compared to 1.1 hours for the regular physical optics. So one can save a lot of computing resources, not only save the memory but also do faster calculations. What that means is that you can go to much higher frequencies in your calculations using large element physical optics than using the regular physical optics. Also, to compare the results between physical optics and large element physical optics, we took the two cuts of the radiation pattern. You can see that both almost agree quite well. And of course, you have good amount of memory savings and the time for the CPU. Another way to hybridize Bethe moments and physical optics or MLFMM and physical optics is to use the iterative method. That is, let's say you take this problem where you have a reflector surface where you can apply physical optics or large element physical optics, and of course you have the feed horn where you could apply Bethe moments or MLFMM depending on how large this feed structure is. And then what we do is that we compute the currents on the feed first using Bethe moments or MLFMM as applicable, and use those currents to radiate into the physical optics region. That is, we consider these currents to be the sources for the physical optics. And from those currents that are generated by physical optics, we again excite the horn and go back and forth. In these iterations, once you converge your currents, then you can compute. One advantage with this one is that remember the n by n matrix we talked about the coupling. So that is not required while taking the coupling into account. That's a great compromise between accuracy and the amount of memory you need. So you get the accuracy, but you don't need the memory that needed for the coupling matrix to be stored. As an example, we applied this to a Cassegrain reflector antenna where we applied physical LEPO to the reflector or the PO to the reflector surface and MLFMM to the feed horn as well as to the subreflector together. And you can see that very nice agreement between regular MLFMM, that is when we apply MLFMM to the whole problem, and the hybrid method where one case we applied physical optics to the reflector, other case we applied large element physical optics. All of them seem to agree quite nicely. You can see the difference in the memory requirement from 12.4 gigabytes for MLFMM to 0.43 gigabytes for a hybrid method. Now let's take a look at the hybrid Bethe moments and ray launching geometrical optics technique and its applications. RLGO or ray launching geometrical optics is used for electrically very large structures, and also when you look at PO may be very good for conducting objects, but RLGO can be good for dielectric objects as well. So it's used for lenses, reflectors, large scatterers as well. Sometimes this is also referred to as shooting and bouncing ray method in the literature. So we can also have Bethe moment structures that can interact with the ray launching at the same time in the picture. For example, here, this could be the lens, this could be metallic structures. All of this could be in ray launching geometrical optics, but you can have an antenna with Bethe moments unknowns there. So one of the disadvantages is that you want to keep the Bethe moments unknowns a little bit far away from the object which we're analyzing because the rays have to reach them. If you're very close, maybe there's a difficulty in launching the rays, and also the rays that are grazing instance could have an issue. So there could be reduced accuracy with the multiple reflections as well. So general philosophy of ray launching geometrical optics is that if you have a source, it could be Bethe moments, triangles or segments or impressed sources. So these things radiate and then they interact with a dielectric object or a metallic object. A fictitious sources or Huygens sources are placed on the surface. For example, this is a dielectric object, but then the interactions are taken into account inside the dielectric, and then equivalent sources are also placed on the other side. So using the equivalent sources, now we can compute radiation patterns and the near fields, etc. in RLGO technique. Just to illustrate how RLGO works, we took a parabolic reflector, and of course the reflector surface itself can be RLGO. We have the feed antenna, horn antenna here. So this can be also be divided into two parts of the program where you can take the horn antenna, analyze it separately using Bethe moments, so you get the radiation pattern, and use that radiation pattern as a source for the reflector. So RLGO can be used on the reflector itself. This we can also call it as domain decomposition methodology that we follow in Altair Feko as well. So this should give you the radiation pattern for the horn, the radiation pattern for the reflector when you compute with the radiation pattern of the horn as a source. How accurate are the calculations? If you take a look at the near fields, which actually requires more accuracy than the far fields, this is with the RLGO with equivalent source, the one we talked about in the previous slide. If you take the method MLFMM with equivalent source, same problem, applying MLFMM to the reflector, this is how fields look like. And of course, the MLFMM with the horn, that is everything taken into account, this is how fields look like. So you can see that there's a very close correlation between RLGO and MLFMM with equivalent sources. That means RLGO can work quite well for these kind of problems. And of course, it can take very less memory, 62 megabytes compared to 4 gigabytes for MLFMM. Of course, it took a little bit more time because of the interactions of the rays that you need to take into account, but nevertheless, it's a very low memory requirement. Similarly, we consider another example of a lens antenna. This is the dielectric lens with a dielectric constant of 6. And of course, we can generate an analytical radiation pattern for cos to the power of 4 pattern. And then we can compute the radiation patterns using RLGO. You can see that RLGO, which is a red line, and MLFMM, that is instead of using RLGO on the lens, we also use MLFMM. They both seem to agree quite nicely, most of the areas, as you can see. And difference being MLFMM takes 15 gigabytes, 8 minutes of the time. RLGO takes 97 megabytes and 11 seconds. Of course, here one want to make a caution that though we're showing the less memory and time, if you can afford, that is, you have 15 gigabytes of memory and you can wait for 8 minutes, I personally recommend that you use MLFMM for analysis. But of course, if you want a quick answer and very less memory, use RLGO as the first cut. Or in cases where you don't have the memory, let's say you only have 8 gigabytes on your computer, you could use RLGO. Of course, you can use other methodologies as well we have in Feko to reduce the memory and CPU time. Also, let's take a look at hybrid method moments and uniform theory of diffraction methodology and its application. So the motivation for using UTD instead of PO or RLGO is that they both are frequency scalable, but at the same time they could be very, very expensive when you get into very, very high frequencies because of the number of triangles and the memory requirements, etc., and the time it takes. For such problems, UTD could be suitable. It's based on ray tracing methodology using reflection, diffraction, and creeping wave calculations. One advantage with UTD is that it doesn't change its CPU time or memory requirement with respect to frequency. We'll see that in a couple of examples here. The way UTD works and also the hybrid method of moments with UTD works is that if you have a plate and you have a dipole in front of it, dipole can be discretized with segments and can be analyzed with the method of moments. So each segments can become, the current on each segment can become a source to the UTD where you compute the reflection from the plate at the observation point, what comes out here, plus also diffraction contributions at the observation point, as well as the direct ray contributions, so giving you the total field because of the reflection from here. Because it's array based and also based on these reflection and diffraction coefficients, which already include the frequency term, it doesn't matter how big this plate is. It could be 10 wavelengths by 10 wavelengths or 100 wavelengths or 1000 wavelengths. It's the same computational cost, memory and the CPU time. That's one big advantage of UTD where you can apply. When you say where you can apply, most of the times UTD is limited to, let's say, flat plates or a one single cylinder, at least in Altair Feko. So if you can approximate your geometry with the flat plates, of course, you can also model the antenna with method of moments. Then you can couple them and do very nice calculations at any high frequency without worrying about memory and the time. As an example, we can take a satellite structure which may look like a CubeSat, for example, at 6 gigahertz. This is around 20 wavelengths in size each side. And there is a little monopole here, lambda by 4 monopole at 6 gigahertz. You can see that if you compute with MLFMM, that's a red line, and UTD, that's a blue line, you get a very nice agreement, despite the fact that the monopole is in the middle of this corner reflector type of structure, which could have multiple reflections, etc. Now the same structure going to 15 gigahertz, 1 meter becomes 50 wavelengths. We could compute that with UTD without any problem. But of course, MLFM could have taken much more memory than what UTD would take. So if you look at the computational cost of 6 gigahertz, that's a previous slide, 14 gigabytes of memory for MLFMM. Of course, we didn't do calculations at 15. UTD will take the same memory at 6 or at 15. You can see that memory is like a megabyte, nothing in terms of memory quantity wise. One last example of UTD, again, when you have a ship platform which can be approximated with the flat plates. Let's say you're putting a radar on the deck of the ship and you're rotating the radar, and you can want to see what is the effect of these obstacles, the mass on the ship. So we created, because this is a 10 gigahertz, that's 4,000 wavelengths and 467 wavelength in length, and the height is 1,000 plus wavelengths, I guess. So you can see that it's a huge problem. You can't do with any of the methods that may be available today, either full wave or asymptotic, except UTD in this case. So we kind of created a radar antenna in like a fan beam using a sectorial horn to represent it, and we could place that on the deck of the ship and want to calculate the pattern, and then see when you rotate this source, how does these obstructions affect your radiation pattern performance. So initially we started with very coarse radiation pattern calculations, and you can see that at 340 degrees the pattern will have a null, big null. If you look at other places, it has got a nice main lobe, but at 340 there is a big null here. So this can be done, for example, with 2 megabytes of memory and 6 minutes per pattern. That is, each one took 6 minutes to compute. Of course, this time in UTD depends on how many points you have in the radiation pattern. Because we have coarse radiation pattern, it took 6 minutes. Of course, if you refine it, it will take more time, but the memory will remain the same. As we can see here, now we have increased the resolution of the radiation pattern. So it still takes 2 megabytes, but takes around 6 hours. But 10 gigahertz, this is a phenomenal in terms of the memory and time-wise, the way you can calculate the very nice radiation pattern for this structure. So the bottom line, I guess, is UTD is very good where it fits well, and also it can scale very well with frequency because it doesn't take too much memory. Of course, the time depends on how many points you want to calculate in your radiation pattern. So far, we talked about individual antenna elements and how we can handle them with the different numerical methodologies and simulation methods that we have. Let's briefly take a look at antenna arrays. How do we analyze antenna arrays using the modeling and simulation? One way to do that is using periodic boundary conditions. They're essentially, if you have a single element and you can put boundaries around it, which essentially analytically duplicate this element to infinity in both directions. So you have an infinite array of these, let's say the helix antenna here we are showing here. This can be done with both FEM or metro moments. Either of the methods can be chosen for this type of analysis. But of course, I'm just showing a dialog box here from our software Feko. You can actually specify the phase shift of each element in the array. So you can actually have the scanning performance of your array. And also in the radiation pattern, you can say how many elements you want to have for finite array analysis. Of course, this is what it is that you calculate the element pattern, and from the element pattern, you apply the array factor to compute the, for example, 21 by 21 array, and it's a beam width as well as side lobes, etc. You can see that normally it does seem to agree quite well with regular MLFMM, But of course, it doesn't take into effect the edge effects of the finite array, etc. But definitely it takes much less memory than trying to solve the large array. Because this memory here does not change whether you take 21 elements or you take 100 elements or 1000 elements, because you're only simply calculating one single unit cell. So how do we analyze finite antenna arrays more efficiently than just say using brute force way of putting all the elements and throwing it a MLFMM or FEM or other techniques? There is a technique called domain Green's function method, DGFM, which is not very well known, but it's a very efficient method for analyzing finite array analysis. So we'll take a look at it briefly in this. So DGFM is based on metronome moments. It accounts for edge effects of the finite arrays, and also it accounts for mutual coupling. The way it works is that all the elements in an array has to be identical, and of course they don't need to be periodic. They can be arbitrarily placed anywhere you like, but as long as each element is identical to the other element, the way it works is that you compute the self element, that is this element, and while you're computing this, because you already know this is also going to look similar type of calculation, you take that coupling into account, this one as well as the other element. So the coupling terms Z12, Z13 are added into Z11. Same thing here. So you are solving very small matrix compared to the big matrix that you need to solve when you take everything into account. I'm not giving all the mathematical details here, but if you're interested, there's a paper in IEEE Transactions on Antennas and Propagation in 2014. You can read this paper. It'll give you more details on the mathematics of this problem. With the DGFM at our disposal, you can actually do a linear array, like regularly spaced elements, in this case open-ended waveguides, or even a cylindrical array. That is, they don't need to be in the same plane. They can be in different planes in a circular or a cylindrical fashion, or any custom array. They don't need to be in a specified one. You can specify different spacings of these elements. So only constraint is that they have to be identical to each other. Each element has to be identical to each other. So you can see that in this case, when we're doing this custom array, if you do with metronome moments, just for 5 elements here, 1.5 hours, and DGFM will take only 30 minutes rather than 1.5 hours. Memory usage, 7 gigabytes to 300 gigabytes, megabytes per DGFM. So tremendous improvement in memory and time as well. Before we conclude our talk, let's look at a couple of advanced topics. One of the advanced topics that is very popular nowadays for antenna analysis is characteristic mode analysis. It gives you the fundamental physical insights that driven simulation does not give you. That means instead of blindly doing the simulation without excitation for any structure, can we find the modes of that structure? It gives you that insight even without an excitation. So you can actually understand the physics of the structure before you can make an antenna out of the structure, like the ones we're showing here with the different modes. No excitation here. It gives you what is mode 1 and mode 2 pattern will look like, and also combination of different modes will look like. I call this as putting physics back into simulations rather than doing blind simulations and finding out the results. You can actually understand the structure and its characteristic modes before you design the antenna. And we published a paper on this in IEEE Antennas and Propagation magazine in 2015. And if you're interested, of course, you can read this paper. And of course, there's a lot of literature on CMA that's available in the literature. And the second advanced topic that's also becoming popular nowadays is machine learning for antenna design and optimization. So this is nothing new. Machine learning has been around for a long time, and computer scientists is a field of study that gives computers the ability to learn without being explicitly programmed. Or you can also think of it as a family of algorithms that help make predictions from data sets. So basically, you calculate various electromagnetic parameters with the different parameter variations and create the data that is needed for machine learning. And so the algorithm learns from the data you generated and creates its own mathematical model that can replace the physical model. So basically, you supply the data, enough data required, so that the machine learning algorithm can learn how your model is behaving and creates its own mathematical model. Once a mathematical model is created, you don't need to run the physics simulation, but you can use the mathematical model to do the optimization, so it can become very, very fast in terms of doing things. If you're interested in learning how machine learning for antenna design and optimization can work, we offered a short course at the 2020 IEEE APS symposium of course, should have been in Montreal, but we did it virtually. And now it's available as an on-demand course with, of course, it's free for everyone to attend at this link. And you have to register so that you can, it's a 3-hour course that you can learn the machine learning for antenna design and optimization. Just before concluding, I want to focus on antenna modeling and simulation in education. As we all know, simulation tools have become everyday life for any antenna engineers or electromagnetic curriculum. But how do we take simulations and fuse with the theory, that's the traditional teaching of antennas, into account so that students become a better engineer, understanding the physics behind the problem, but also understanding the tool, how to use the tool effectively to solve a problem. So we take a case study with the University of Michigan Dearborn, where one of the instructors was simulating the experiment with our tool Altair Feko and correlate the simulation results with theory, and then let students do the experiment in the lab and correlate the measured lab data with the theory and simulations. And this is how his lab looked like. So you have simulations that is done ahead of the experiment. That is, whatever experiment you're doing, you simulate first. You ask the students to simulate so they understand how simulations work. And in the lab, you explain the theory behind it. This is a coupling between two loop antennas, and the theory, though you can't see it here, you can write the equations to understand how that works. And then you do the measurements, or you let students do the measurements, understand the relation between experiment, theory, and the simulation. That way they have the complete picture of how these things work, and they look at the tool, simulation tool, as a tool rather than a solution by itself. And to me, I guess, is the students are the solution who can think and understand the physics and then apply the tool appropriately for their problem. For those of you who are students and faculty in this audience, Altair University, where we offer Altair Feko Student Edition free for students and faculty. You can download them at altairuniversity.com/Feko Student Edition. So all the technologies I talked about, the tools for simulation modeling, are available in Feko, and you get to experiment that with Student Edition if you're interested. Also at the same place, the link that is given here, we have a free ebook that you can download that gives you various examples if you're using the tool, how to learn the tool using examples with the video tutorials and those kind of things. If you're interested in using a textbook using simulation tool, we have a book, Antenna Analysis and Design Using Feko Electromagnetic Simulation Software, co-authored by myself and Professor Elsher Beni and Professor Payam Nayeri from Colorado School of Mines. You could potentially use this as a supplementary book or a main textbook. Of course, this is, I call it as an antenna book without equations, because we're going to learn antennas, different type of things I'm listing here, through simulations. It's available on Amazon and published by IET, Institute of Engineering and Technology in England. In this talk, we discussed many different technologies, full wave techniques, asymptotic techniques, hybrid techniques, array analysis, etc. Of course, if you are interested in reading more about them, a little bit more in depth than what I presented here, one of the books I would like to recommend is Computational Electromagnetics for RF and Microengineering. This is especially written for the users who are using the tools, so like Feko, for example, to learn the methods behind the tools rather than someone who want to know all the mathematics and write the codes themselves. So my recommendation would be this book if you want to probe more about numerical methods, written by Dr. Professor David Davidson. Of course, the another one we also contributed myself and Professor Kubilai Sertel from the Ohio State University in the Handbook of Reflector Antennas and Field Systems, Volume 2, a chapter called Numerical Methods. If you already have the book or you want to get this handbook written by, edited by Dr. Sudhakar Rao, Professor Shafai, and Professor Sharma, we have a nice chapter in there, of course, mainly focusing on the reflector feed systems and reflectors there, which also explain different methodologies that I covered in this. With that, I would like to thank you very much for your time for this attending this talk. If you have any questions, you can write to me at my email address, cjreddy, cjreddy at altair.com. I'll be more than glad to answer your questions. Thank you.